Okay, so just going around the room, everyone had that the inverse of x was equal to the cube root of x, was it minus 4? Yeah. Okay, good work. So moving on to example number 3, we have a function x squared minus 4. You guys could start by just graphing that parabola.
That's parable, isn't it?
You got it, Booker. Okay, so we're going to graph it. We look here, the y-intercept's at negative 4. It's also going to be our minimum. Careful with the scale. It's going up and down by 2s. Okay, we have scales of 2. And if you were to factor this, x plus 2, x minus 2, you would have your x-intercepts at 2 and negative 2. So without even using your calculator, you should be able to draw that function. So Bruce, what would your domain of the parabola be? Any real number? So from negative infinity to infinity, okay?
I think that looks right.
Thank you. Okay, Brett, how about the range?
Negative 4 greater than negative 4. You want it in that notation or?
Sure. What you said was correct. Good, so our minimum is at negative 4, so y is greater than or equal to negative 4. Okay, so now we have to figure out, what does this mean? X equals f of x. What's another way of describing that? Find the inverse. Oh, you guys are smart. Okay, so we just went through all the steps on how to do that. First, we're going to let f of x equal y, and that equals x squared minus 4. Then we're going to switch the x and the y. So x equals y squared minus 4. And then we solve for y. So add the 4 over, we get x plus 4 equals y squared. And we have to get rid of the square, so we're going to square root. We get the square root of x plus 4. Thank you. Can I ask, what have I forgotten? Plus and minus. You always have to take the positive and the negative square root. So this is our original parabola. What I'd like you guys to do is go into y1, y2. If you want, you can use your mirror line as well. Keep in mind, I still have this on my calculator, so I've got to clear this all off. And your y1 you're going to clear as well. Your y2 clear out. Then we're just going to put in the two functions. So the positive square root of x plus 4. And the negative square root. Don't forget to use the negative sign, not the subtraction sign. In front of the square root. So it's reflected in our mirror line, y equals x, and now we have a sideways parabola. Just going into part C here, let's talk about the domain and range before we actually put it on our graph. Okay, so the original function had a domain of x's and elements of all real numbers. The range was that y had to be greater than or equal to negative 4. So the domain of the inverse function will come from the range of the original function. So the domain will be x is greater than or equal to negative 4. So I just mark that on my graph at negative 4. And the range will come from, so So the range of the inverse will come from the domain of the original function. So that will be an element of all real numbers, which means y will go forever to infinity and to negative infinity, or beyond. Alright, can we say that the original graph was a function? We all agree?
Yes.
So f of x is proper notation? What about our inverse? If we did the vertical line test, would it cross through more than once? So it's not a function. Okay, x repeats. And this is a little skill testing question. So we figured out the inverse is not a function. How could the domain or range of the original function be restricted so that the inverse graph, would actually be a function? It's a tricky one. Dawson? On the inverse or the original? Okay, so if I restricted the range of the original one so it didn't go past 0, you would still have a little mini prad left. So if you switched it, you'd still have a relation, not a function. Remember we talked about the positive and negative square root? So let's just say we restricted the domain of the original function to just the positive side of the parabola. If we did that, then the inverse would only give us the top half there. So if we restrict the domain to say x is greater than or equal to 0, then it would also restrict the inverse to just the positive piece. So that was a bit of a tricky question, but just wanted you to think about how you can manipulate these graphs to get the results that you want, so if you did want a function. So this next question is kind of similar. So Don incorrectly determined the inverse of a function defined by y equals the square root of x minus 3 to be the equation y equals x squared plus 3. Okay, well, if we take a look at this graph, okay, it's going to be like this. Okay, if I take a look at the parabola, it will look like this. How is this the inverse of this when there's only one piece to that? But there's two on here in the parabola. What did Don mess up? Good. So this is just the positive square root of x minus 3. So so he's saying that this is the inverse. Okay, what restriction would we have to put on the parabola? Okay, the parabola would have to be that x is greater than or equal to 0. We put a restriction on that domain. And if we do that, then we only are, so it'd have to be, that's reflected. Yeah, we're good. Okay, x is greater than or equal to 0. It's just the positive piece. So we can put that restriction to match what the original function looked like. Okay, lastly, if you're ever unsure if you have come up with the correct equation for the inverse of a function, there is a way to test it. Truthfully, I think it's a little bit more work than it is worth, but there is a statement that is true. Okay, so I'll just read the final result, what you're going to discover. Basically, two functions, f of x, g of x, are inverses of each other if the composition of f of g of x is equal to x, as well if you were to do the opposite composition, g of f of x, it will also equal x. So if you do that, and they both equal x, then they are in fact inverses of each other. So just as review, because this is a big part of the unit, compositions are heavily tested on your unit test. So let's just go ahead and try f of the inverse of x, or f of x. And then we're going to do the inverse of f of x. Before we can do these compositions, what do I need to solve for? They've given me f of x. What do I need to do these compositions? Jared, what do you think? I noticed. There's lots of chit chat. We're given f of x. We need to take two compositions that include the inverse of f of x. So obviously we need to find f of x first. So let's do that over here. So first we're going to let f of x equal y. Then we switch the x and the y. And then we solve for y. And we've actually done this one already. We get y is equal to x plus 3 over 2, but we have to note that y is actually the inverse of f of x. So now that we have the inverse, it's a little bit easier to do these compositions. So the first one is f of the inverse of f of x. So what was the inverse of f of x? It was x plus 3 over 2. That is going to replace every x in the function f. So the function f of x is described as 2x minus 3. So we're going to get 2 times x plus 3 over 2 minus 3. What's lovely about this one is the 2's cancel out as well, and so we're left with x plus 3 minus 3, and then the 3's cancel out. So we're left with x. And that's what we wanted. We wanted to prove that they're inverses of each other. So we've got an x for this one. We need to prove that the inverse of f of x is also equal to x. So subbing into the inverse function, we're going to put f of x in there. F of x was 2x minus 3. So we're going to sub 2x minus 3 into every x from the inverse of f of x. So 2x minus 3 is replacing the x, and we have to add 3, all divided by 2. In the numerator, we have 2x minus 3 plus 3, so we're left with 2x. In the denominator, divided by 2, 2's cancel out, and we have x. Thus, we have proved they are inverses. Okay? If we have the inverse of f of x is equal to x, and f of the inverse of f of x is also x, they're inverses. Cool?
Very cool.
Oh, fantastic.